Hey, what's up guys? I hope y'all are doing well. Welcome to another video where today I'm going to talk a little bit about this second type of induction problem that IB really likes to use. So this is where IB's asking us to prove that some sort of given function is always divisible by some sort of given number. For instance, this might be really easy, but for instance, if they wanted us to prove like 2x plus 4 is divisible by 2. So that'd be an example of this problem, although it'd probably be a bit harder than that. That being said, I do want to say something about these sorts of problems. I won't say that they're super easy, but the trick to these problems is that there's really only one method to actually solving this problem. So there really aren't that many tricks for IB to throw at you. So if you kind of understand how to solve one of these problems, I think you can solve all of them. So one tip I'm going to give is that when you're solving a sort of problem like this, what you want to do is, well, IB is going to give you some sort of function, right? We'll call that f of x. What you want to do is, when you're doing your inductive step, you want to turn f of x into a polynomial. You always want to turn f of x into a polynomial, and that's the key. So the reason you want to actually do this is because it's actually super easy to prove that a polynomial is divisible by some number, right? So let's say we have the polynomial 3x squared plus 6x plus 12, I don't know. And for some reason, we needed to prove that this is divisible by 3. Well, that's super easy to do. We can just factor out a 3, and we're left with x squared plus 2x plus 4, which is clearly an integer, if x is an integer, and when you divide this entire thing by 3, you're just left with x squared plus 2x plus 4, and you've basically just proven that it's divisible by 3. So let's use this tip in action, and let's actually do a problem from an actual past IB exam. So in this problem, we're being asked to use induction to prove that 4 to the n plus 15n minus 1 is divisible by 9 for all n such that n is a positive integer. So before we can actually use that tip, what we have to first do is we have to tackle the base case. And remember, our base case is basically, well, we just take the lowest possible value of n, and that value of n is 1 because 1 is the smallest possible positive integer. And what we're going to do is we're going to substitute that into our original equation. Doing so gives us 4 to the first, which is just 4, plus 15 times 1, that's just 15, minus 1, and we're left with 18. Now clearly 18 is divisible by 9, so our base case is satisfied. So next what we'll do is we'll take a look at the inductive hypothesis. So remember, the inductive hypothesis is where we assume that the statement above is going to be true for all n is equal to k. So assume truth when n is equal to some k. And what does this mean? Well, what this means is when we substitute n as k in our equation, so that will look like, I'll use a different color, substituting all the n's as k's, we're assuming that this guy over here is divisible by 9. And how do we actually write that algebraically? Well, what we're going to do is we're just going to write equals times, do something a little clever here, times 9a. Now, why can we actually do this? Well, if 4 to the k plus 15k minus 1 is divisible by 9, that means when we divide it by 9, we're going to get some remainder that is an integer, right? And I'm just going to let that integer be a. So I'm just going to let a be some, I don't know what the integer is, but some random integer. So hopefully that makes a bit of sense as to why we can do that. So now on to our inductive step. That's basically where we want to prove truth holds when n is equal to k plus 1. And what does that mean? Well, that just means when we substitute n is equal to k plus 1 in our original equation, that guy is going to be divisible by 9. So let's do that really quickly. I'll use a different color again. So 4 times k plus 1. Again, we're just substituting all the n's as k plus 1's, plus 15 times k plus 1 minus 1. And again, we want to prove that this guy is divisible by 9. Okay, so how do we actually do this? Well, let's go back to our tip over here. Remember, we want to write every function as a polynomial. And the problem is, right now, this isn't a polynomial because we have an exponential term. So we want to get rid of that exponential term. How do we get rid of that exponential term? Well, this is where our inductive hypothesis comes in. We're going to bring this guy over down here. And what we're going to do is we're going to take a look at this term. What we can actually do is we can isolate this term in terms of a and k. And when we do that, we can actually resubstitute that back into this equation, and we can get rid of all the exponential terms. So let's take a look at what that actually looks like in practice. So I'll write it in another color. Well, 4 to the k plus 15k minus 1 is equal to 9a, right? Well, how do we isolate for 4 to the k? Well, we're just going to bring the other two terms to the other side. We're left with 4 to the k is equal to 9a minus 15k plus 1. And now we want to resubstitute this equation back into here, as I indicated already. But there's a small problem. The problem is that, well, we have 4 to the k in this equation, and we have 4 to the k plus 1 in this equation. But what we can do is, well, we see that 4 to the k plus 1 is just really 4 times 4 to the k, right? That's just 4 times more than 4 to the k because of exponent rules. So what we can do is we can actually rewrite our green equation, and we're left with 4 to the k times 4, and make sure you see why we can do this. 4 to the k times 4 plus 15k plus 1 minus 1. And in order to get rid of this exponential term, I'm just going to borrow the equation that we used here and resubstitute it in. So doing that, we get, I'll write that one term in a different color. We get 9a minus 15k plus 1. So that's the term we substituted in. We're multiplying all of that by 4. And then we're adding 15k plus 1. Well, that's just 15k plus 15. And then we're finally subtracting 1. So now let's simplify this. Let's expand everything out and let's collect like terms. So doing so, well, 4 times 9 is 36, so we have 36a. 4 times 15 is 60k. 4 times 1 is 4 plus 15k plus 15 minus 1, well, that's just plus 14, of course. All right, equal signs here. So there's only one term that has an a, so we'll just copy that down here. So negative 60k plus 15k, well, that's just negative 45k. And finally, 14 plus 4, well, that's just 18. And we have the polynomial that we're looking for. So again, we want to prove that this polynomial is divisible by 9. How do we do that? Well, that's super easy. We know how to do that. We're just going to factor a 9 out. And we're left with 4a minus 5k plus 2. Oh, that's supposed to be k. And because a and k are positive integers, we know that 4a minus 5k plus 2 is a positive integer. Thus, we have proven our inductive step because this guy over here is certainly divisible by 9, because then the 9 just cancels out. The red 9 just cancels out. So we can finally say that, hey, because we've assumed that when n is equal to k, it's true. Now that we've proven when n is equal to k plus 1, it's true, and we know that when n is equal to 1, it's true, then we can say that for all positive integers n, this statement is true, and we're done.